Now that we've spent some time with stoichiometry and reaction stoichiometry, we need to up our game a little bit. And so we're going to start talking about excess and limiting reactants. So when we do a reactant, so far all the examples we've done have had one reactant in excess, meaning that one reactant has been limiting and all used up. We've very intentionally written it that way. But that's not always the case. Sometimes we know how much we're mixing of each thing, and we don't know what we call the limiting reactant is. We don't know which one the limiting reactant is or which one the access is, and we need to be able to figure that out. So, what if we're given amounts for both reactants in a reaction? How do we decide how much product we can make? One of the reactants will be completely consumed or reacted. That's known as your limiting reactant. It limits how much product you can make. The other reactant will be present in excess, meaning some reactant is left over at the end of the reaction. The reactant that limits the amount of product that can be made or produced is known as your limiting reactant. The amount that is left over in excess is known as your excess reactant. Okay. So common questions we get is what chemical is limiting reactant, how much of the excess reactant remains after completion of the reaction, and how much product can be formed. In order to answer that third question, you actually have to figure out the limiting reactant first so that you can figure out how much product can be formed. So let's do some examples. First up, let's just really set some clear definitions here so that we're all on the same page. Limiting reactant, again, also known as limiting reagent. Reagent may be used in place of reactant, but it's the reactant that's completely consumed or used up in a reaction. It also limits the amount of product that can be produced because it's all used up itself. The reactant in excess, or what I call excess reactant, is any reactant that's in a quantity greater than required to completely react all of your limiting reactant. Your theoretical yield is the amount of product that can be produced in a chemical reaction based on that limiting reactant. Your actual yield is how much product you actually isolate from the reaction. Actual and theoretical, you want them to be close, but you probably are going to lose some product somewhere throughout the process. Percent yield, how much product did you obtain from a reaction in percent form? So you take your actual yield, divide it by your theoretical yield, and multiply that by 100% to get it in a percent form. And then another concept you may encounter is atom economy. I personally am not going to test you on this concept, but it is an important concept to understand that scientists and chemists as a whole are thinking about. And it's how many atoms in the reactants become atoms in the products. So you take the molecular weight of your desired product and divide that by the molecular weight of all reactants that go in to make it, multiplied by 100%. The reason it's an important concept is it deals with green chemistry and sustainability ideas. So basically, the idea is let's find better routes of chemical reactions so we're not using a bunch of stuff that's going to go to waste. The percent yield only looks at the product you're interested in and how much product you make. It doesn't look at all the side things that go into it, all the reactants that have to go into making the reaction proceed. Whereas atom economy looks at everything that goes into a reaction. Okay, limiting reactant. We're going to use a Chick-fil-A sandwich to describe a limiting reactant because most people have seen a Chick-fil-A sandwich. Chick-fil-A sandwiches, the recipe for a sandwich is two pieces of bread, the top and bottom of your bun, one piece of chicken, and two pickle slices. Okay? So if I told you, if this is what your Chick-fil-A sandwich should look like, and I say, how many sandwiches can you make with 8 pieces of bread, 5 pieces of chicken, and 10 pickle slices? Most people very quickly can tell me, well, I can only make 4 sandwiches because I only have 8 pieces of bread. I only have 4 buns equivalency. So you can just very quickly say, this is my limiting reactant. The amount of bread I have is going to limit how many sandwiches I can make. We're going to say the chicken and the pickle are in excess because I have more chicken than I can make sandwiches and more pickles than I can make sandwiches. But what if we did this mathematically? Well, let's treat our bread as we're going to do a lowercase br, just because we don't want to confuse it with the elemental element bromine. For chicken, I'm going to do lowercase c, lowercase k, and for pickle slices, I'm going to do a pi. Okay, and they are going to make a sandwich, which I'm going to call SD. So let's do the stoich here. Number of sandwiches I can make with my bread. I have 8 pieces of bread. Every one sandwich requires 2 pieces of bread. Therefore, I can make 4 sandwiches. What about with my chicken? Number of sandwiches? I have 5 pieces of chicken. Every one sandwich requires 1 piece of chicken. So I can make 5 sandwiches from my chicken. And let's find a different color here. And what about my pickle slices? Number of sandwiches? I have 10 pickle slices. Every one sandwich requires 2 pickle slices. So I can make 5 sandwiches. Okay? So we again can see very, very quickly that we can only make 4 sandwiches with this setup. On the description we've given here, my limiting reactant is my bread. My access reactants, I have 2 of them here, is my chicken by 1 chicken and my pickles by 2 slices. So we're going to do that same thing, but we're going to do it in the respect of chemicals instead of Chick-fil-A sandwiches. But it really is that quote unquote simple. Okay, this looks overwhelming and daunting, and I get that, but I need you guys to trust the process, okay? This is the process I want you to follow until you get comfortable doing these. There are other ways to solve these questions. I do other ways in my notes myself. But if you are unfamiliar of doing this or you're not the best at doing these calculations, do it like this first until you get your patterns down, okay? If you have another way and it always works for you and you're good at these problems, that's fine. But if you don't follow this step by step, and it will get you to the right answer. So step 1, convert what you're given to moles. Any information you're given, convert it to moles. Step 2, ask yourself, if you use up all of one of the reactants, how much of the other reactant would you need? Step 3, answer the question in step 2 using your mole to mole ratio from your balanced reaction. Step 4, ask yourself, do I have it? Do I have enough? This is based on questions 2 and or steps 2 and 3. Assign labels limiting or in excess for the 2 different reactants you have. And then step 6, using your limiting reactants, solve your original stoichiometry problem. So let's go through an example like this. In a commercial process, nitric oxide, NO, is produced. What mass in grams of NO can be made from the following reaction? I've got 30 grams of ammonia reacting with 40 grams of oxygen gas. Now, let's write out our balanced reaction because we definitely did not give it here. Okay, so depending on where you are in the semester, I may or may not give you a reaction. Um, Sometimes I do, sometimes I expect you to be able to use the species that we have and predict the product. We haven't gotten to predicting yet. So in this case, I would give you this reaction if we got to, if the assessments happened before we got to reaction predicting. So your reaction here is 4 moles of ammonia reacts with 5 moles of oxygen gas to produce 4 moles of NO gas and 6 moles of water vapor. The other thing I recommend you do, but you don't have to do, okay? I can't require it. Well, I could. I choose not to require it, but I highly encourage you to do this. Is when you are given a process like this, underneath or above the reaction, wherever you want to write it, write down what you're told. You are told you have 30 grams of the NH3 and 40 grams of the O2. The reason I encourage you to write that down is that it very quickly shows me it's a limiting reactant problem. How did it do that? I am given an amount of 2 reactants. I only have 2 reactants. If I had more than 2 reactants, I'd give you, that statement would hold a little bit better. But when you are given amounts, for 2 or more reactants, it's a limiting reactant example. So it very quickly identifies for me that it is, in fact, limiting reactant example. Okay. Step one says convert what you're given to moles. So we're going to convert everything we're given to moles. So number of moles of ammonia. I have 30 grams of ammonia. I add up the molar mass. Nitrogen is 14.01 grams per mole. Hydrogen is 1.008 grams per mole. And I have 3 hydrogens. So overall, this comes to 17.03 grams of NH3. This gives me 1.762 moles of NH3. Do the same thing with your other reactant. I need to know the number of moles of O2. I have 40 grams of O2. 1 mole of O2 weighs 32 grams. 1 oxygen is 16 grams per mole, so 2 oxygens is 32 grams per mole. This gives me 1.250 moles of O2. Notice I'm putting that 0 here because I can keep my sig figs, okay? So I've done step 1. I've converted everything I have to moles. Step 2, ask the question, if you use up all of one of the reactants, how much of the other one will you need? Truthfully, it doesn't matter which one you pick, okay? I pick them randomly. Sometimes it works to my advantage, sometimes, well, either way, it gives me the information I need, okay? Either way, this will tell me the information I need. So I'm going to compare the two reactants to one another. For this one, I'm going to write down number of moles of NH3 needed to react all of my O2. I have 1.250 moles of O2. So how many moles of ammonia will it take to react all of that? I need my balanced reaction. I see that 4 moles of ammonia are consumed for every 5 moles of O2 consumed. This tells me that I need 1.000, sig figs here, don't lose them, moles of NH3. So I've done step 2. I then ask myself, and I've done step 3. Ask myself, do I have it? Do I have enough? I need 1.00 moles of NH3. I have 1.762 moles of NH3. Yes, I have enough. I have enough ammonia to completely react all of the oxygen present. So that tells me that this is my access reactant because I have more than enough. This is my limiting reactant because it's going to run out. I have more than enough ammonia to react all of it. Now, if I had done it the other way, if I had solved for how much oxygen to react all of my ammonia, I would have realized I didn't have enough oxygen. And that would have also told me that oxygen was my limiting reactant. I do have to make some space for us. So 1 second while we do that. Okay, so now we got some space. So I have also done this and I've done this. Now I can use that limiting reactant to solve the original stoic example or stoic question. Now that we've determined the limiting reactant, we have to figure out what the original question was because I don't remember anymore. What mass in grams of NO can be produced from this reaction? Okay, your limiting reactant determines amount of product produced because it runs out first. So since O2 is the limiting reactant, we're going to use that to determine the theoretical yield. Number of grams of NO, and I've got 1.250 moles of O2. Looking at my balanced reaction, 4 moles of NO are produced for every 5 moles of O2 consumed. But I'm not stopping at moles. I don't want moles. I want grams here. So I add up the molar mass of NO. nitrogen is 14.01 grams per mole, oxygen is 16 grams per mole, so it's 30.01 grams of NO for every 1 mole of NO. And I get 30.01 grams of NO produced. So the 1.25 times 4 divided by 5 happens to equal 1, and that's why it happens to equal 30.01 grams. It's producing exactly 1 mole of the NO. Okay. Measuring success for reaction. The amount of product collected at the end of the reaction is called your actual yield. How much did you actually isolate?
This amount is often less than the yield that we predict we should be getting from the reaction stoichiometry. What you just did was the reaction stoich, okay? Which is your theoretical yield. So this is calculated. But we do this, we present the efficiency of a reaction 2% yield. So again, your actual experimental yield is what you collected. Your theoretical yield is what you calculated. So that theoretical yield involves that stoichiometry calculation. That's what you just did. How much product should you theoretically obtain from the reaction? Some people may ask, why is percent yield of the reaction never 100%? If it is greater than 100%, it means your sample's very impure. It's still probably a solvent in it, most likely water if you're in the Gen Chem world, or different solvent depending what you're using. If it is over 100%, you definitely have impurities there. Something is mixing in that shouldn't be there. But oftentimes you're going to see that your reaction never actually reaches 100, and this is due to things like some reactions don't go to completion. In fact, a lot of reactions don't actually have to completion. They go to an equilibrium state, which we will spend more time on equilibrium in Chem 2. You could have impure reactants, so therefore the amount of reactant that you thought you had to start was actually less than the amount you actually had. When I buy chemicals from a chemical supply company, I often buy things that are 97% pure, 98% pure. I don't buy 100% pure. It just costs too much. Being 97 or 98% pure still gets us the efficiency that we need. But so you may not have everything you need that can actually react, or you could cause other side reactions may happen that can cause other products to form that aren't part of your desired product. And some of the product can just be lost through things like filtration or being left in a beaker, reaction not going long enough, etc. There's lots of ways that this can happen, and it's very common. let's take this example. In this reaction, magnesium solid is reacted with iodine solid for magnesium iodide solid. If 10 grams of magnesium metal reacts with 60 grams of I2 solid and 57.84 grams of MgI2 form, what is the percent yield? Okay, well, let's see, we've got 10 grams here, and 60 grams here. That means it's this limiting reactant example. I know how much I collected. This is my actual. I need my theoretical yield. I don't know what my limiting reactant is yet, though, because again, I have both possible species here. So, you can go through the full six-step method like we talked about. I'm gonna do it slightly different than that. I'm just gonna compare one to the other directly. Again, if what I'm doing does not make sense, come see me for help, or do it in the process that we talked about with the six-step process. Okay? It will get you the same answer. What I'm gonna do though is I'm just gonna say how many grams of magnesium do I need to react all of my I2. So I'm going grams of one to grams of the other. I have 60.00 grams of I2. Why am I picking it this way? Because magnesium is listed first, and I just happen to write it down first. Truthfully, there's nothing special about the way I pick it. When in doubt, convert to moles. 1 mole of I2 is 253.8 grams of I2. Iodine is pretty big molecule. It's pretty heavy. Based on my balanced reaction, I see that 1 mole magnesium metal reacts with 1 mole of 1 mole of I2. Definitely ran out of room, so if you're writing this out on paper, this should go right next to it. Now that I got moles magnesium, I'm going to convert that to grams of magnesium. 24.31 grams of magnesium is 1 mole of magnesium, and that is straight from the periodic table. This gives me an answer of 5.75 grams of magnesium. But what does that mean? It means I need 5.75 grams magnesium to react all 60 grams of my I2. And that may seem, students may think really only 5 grams, but remember I2 is very, very large, so 60 grams of it is not that many moles of it because it's such a large molecule. But this also means is that this is my limiting reactant and this is my access reactant. Because I have more than enough magnesium to react all of my I2, magnesium is my access reactant. I2 is my limiting reactant. So to find out the grams of I2 magnesium iodide that I can actually produce, I'm going to use my grams of I2 because that is my limiting reactant. So number of grams, MgI2, I've got 60 grams of I2. I know that 1 mole of I2 weighs 253.8 grams, partly because I just used it. I know based on my balanced reaction, 1 mole of MgI2 is produced for every 1 mole of I2 consumed. I've
Let's try to combine everything we've been learning into one problem. Here we see we have a four-part problem, A, B, C, and D. Not all problems will be broken up this nicely for us. Sometimes it's just going to ask us one part of the question, and we're going to have to recognize that we need to do all these parts. But it is nicely broken up for us, so let's take advantage. First, part A, write the complete balanced reaction of aluminum reacting with iodine to form gaseous aluminum iodide. Okay, first thing you need to do is write down what the chemical formulas are of the species you're interested in. I know aluminum is Al, and it's a metal on my table, and all metals except mercury are solids. I know iodine is one of my diatomics, so I know that means I2. Now, iodine is one of my nonmetals, and nonmetals can be solids, liquids, or gases. But I do know that bromine and mercury are the only two liquids on my entire table. Iodine is below bromine on the table, which means it's going to be a more condensed phase. So I2 is actually going to be a solid phase. And then it does tell me gaseous aluminum iodide, so AlI3 in the gas phase. So I have all my pieces and I have them with their phases. Now what I need to do is figure out the balancing. I do have that combination 2-3 going on here that we've talked about before when balancing. So because of that, I'm going to go ahead and balance that iodine right away because it's going to mess up everything else. And the lowest multiplet here is to put a 3 in front of the iodine and a 2 in front of the aluminum iodide. This does change the number of aluminums I have, so I need to put a 2 in front here, and now I have it balanced. 2 moles of aluminum react with 3 moles of iodine, I apologize, to form 2 moles of aluminum iodide. So part A, done. Part B, calculate the theoretical yield in grams of aluminum iodide from the complete reaction of 18.3 grams of aluminum and 113 grams of iodine. So I am trying to react, let's see, 18.3 grams here and 113 grams here. I don't know what my limiting reactant is though. So first thing I need to do is figure out my limiting reactant before I can even answer this question. Now, again, if you are not comfortable with the process yet, do the full 6-step method and it will get you to the right spot. I take a shortcut to that and just convert grams from one reactant to grams of the other to see if I have enough. And that very quickly tells me what my limiting reactant is. So I'm going to do it my way, but again, if you are unclear, follow that six-step method. I'm going to find the number of grams of aluminum I need. How many grams of aluminum do I need to react all of my iodine? I have 113 grams of I2. Again, you could have done it the other way and said how much iodine to react all the aluminum. It doesn't matter. Right now, we're just trying to figure out the limiting reactant. 113 grams of I2. I cannot compare things through grams. I can only compare through moles. So I'm going to go ahead and convert to moles. Because again, grams tell you how much of you have something by mass, yes. Remember, a molecule of I2 does not weigh the same as an atom of aluminum. I2 is really an iodine molecule, iodine atom itself is a lot bigger than aluminum, and then you have two of them as well. So, when in doubt, convert to moles. It's probably the right step. 1 mole of I2 weighs 253.8 grams. This step cancels my grams of I2, and now I have moles of I2 present. But I don't want moles of I2. I want to know how many grams of aluminum I need. So I'm going to use my balanced equation, and I see that 2 moles of aluminum are reacted or consumed for every 3 moles of I2 reacted or consumed. So again, this cancels out my moles of I2. Now I have moles of aluminum present. Now that I have moles of aluminum, I'm going to go ahead and quickly convert to grams of aluminum using the molar mass of aluminum. I look at the periodic table, and there's 26.98 grams of aluminum in every 1 mole of aluminum. Again, I got that number straight from the periodic table. This cancels out my moles of aluminum, and now I've got grams of aluminum if I do the calculation. Put this in my calculator, and I get 8.01 grams of aluminum. But remember what that means. It means I need 8.1 grams of aluminum to react all of my I2. And so I ask myself, do I have enough? Yeah, I do. I have 18.3 grams. So I have enough, which means this is my access reactant and this is my limiting reactant. I haven't answered the question yet for part B specifically, but I had to do this first before I could answer that question. Okay? So now let's go ahead and actually answer the question. I want to know the theoretical yield in grams of aluminum iodide. So I want to know how many grams of aluminum iodide I can produce with this reaction. I know I2 is my limiting reactant, so I'm going to start there. 113 grams of I2. And because I didn't follow the six-step method, I do not have the mole of this yet. I'm going to have to redo this step. 1 mole of I2 weighs 253.8 grams. Looking at the balanced reaction, 2 moles of aluminum iodide is produced for every 3 moles of I2 consumed. But I don't want moles, I want grams. So I add up the molar mass here, and it's a pretty big compound because I've got 3 iodines in there. It's 407.7 grams of AlI3 for every 1 mole of AlI3. Make sure your units have canceled. Grams of I2 cancel, moles of I2 cancel, moles of AlI3 cancel. And when I complete this calculation, I get 121 grams AlI3. Again, that is what we call your theoretical yield. That means if the reaction is perfect, I could theoretically produce this much. And it is based on your limiting reactant. Always check sig figs. I always forget to mention that at this point in the semester, but you do have 3 sig figs here, 4 sig figs here. This is exact. 4 sig figs here, so 3 sig figs here. 3 sig figs, 4 sig figs, exact, 4 sig figs, and 3 sig figs. Okay. Well, let's see. We've answered the first one. We've answered the second one. Part B is 121 grams of AlI3. And to answer part B, we've actually answered part C as well. Which substance is the limiting reactant? I2, also known as iodine. Not iodide. Iodide is the ion, iodine is the molecule. And then the last part, what is the identity and amount of excess reactant left over at the end of the reaction? Well, we know the identity. The identity is aluminum. Well, how much is left over? Because of the way we did the math, it actually is quite easy to tell how much is left over. We have 18.3 grams of aluminum available, and we need 8.01 grams of aluminum to react all of our I2. This gives us 10.3 grams of excess aluminum at the end of the reaction. So we've got our balanced reaction. We've got our theoretical yield. We've got our limiting reactant. And we've got our excess reactant identity and amount. Working problems like this is a good practice for you guys, okay? They're not easy. They're not always nicely broken up like this, but you guys should be working a lot of problems like this, okay? What about the next one? Okay, another four-parter. Write the complete balanced chemical reaction based on the following description, okay? Solid aluminum iodide reacts with solid potassium to produce this solid aluminum and potassium iodide. Okay, so solid aluminum iodide. Well, we just dealt with aluminum iodide. So Ali3, solid, reacts with solid potassium. It just says potassium, so it must be potassium metal. Okay, solid. And this produces solid aluminum and potassium iodide. Potassium iodide is a solid as well. Let's balance this reaction out. I see that I have 3 iodine on one side, so I need 3 on the other. This gives me 3 potassium on the product side, so I need 3 potassium on the reactant side. And I have 1 aluminum on each side, so that is balanced out correctly. What is part B? So you got part A, part B. What quantity in grams of aluminum are produced if 150 grams of aluminum iodide are reacted with 150 grams of potassium? Okay, it's got 150 grams of each. I don't know what my limiting reactant is. I have no idea, but it's definitely going to control my theoretical yield. So just like before, I'm going to say, okay, well, how many grams of aluminum iodide do I need to react to all of my potassium? I have 150 grams of potassium. 1 mole of potassium weighs 39.01 grams potassium. Again, I get that straight from the periodic table. I look at the balanced reaction, and I see that 1 mole of aluminum iodide reacts with 3 moles of potassium. Convert that to grams. 407.7 grams of Ali3 is 1 mole of Ali3. So grams potassium, moles potassium, moles aluminum iodide. Calculate this out, and I get an answer of 522.6 grams of Ali3. This is what I need to react all of my K, all my potassium. So do I have enough? No, I only have 150 grams, and I would need 522 grams. That tells me that this is my limiting reactant, and this is my excess reactant. So now that I know that, I know what I can use to figure out how much aluminum I can actually make. Number of grams of aluminum metal will be based on that 150 grams of the Ali3 instead of the potassium, because the Ali3 is my limiting reactant. So 1 mole of Ali3 weighs 407.7 grams. Based on my balanced reaction, 1 mole of aluminum is produced for every 1 mole of aluminum iodide consumed. 26.98 grams of aluminum to every 1 mole of aluminum. And it's always good to check to make sure units canceled. Grams of aluminum iodide, moles of aluminum iodide, and moles of aluminum. So I am in grams of aluminum as I had wished. And I get out an answer here of 9.926 grams of aluminum. And again, this is your theoretical yield. This is how much you could make if the reaction was perfect. So 9.926 grams of aluminum can be produced. Part C says if 9.3 grams of aluminum were collected, what is the percent yield for this reaction? So this means your actual yield is 9.3 grams. So remember, percent yield is equal to your actual yield divided by your theoretical yield times 100%. So I actually collected 9.3 grams of aluminum, but theoretically I could have made 9.926 grams of aluminum. So my percent yield here, 94%. I've got 2 sig figs here versus 4 sig figs here, so my final answer can only have 2 sig figs. So 94% is my percent yield if 9.3 grams were actually collected. Now, I'm going to have to shrink this stuff down to be able to fit part D on this slide. Okay. If the percent yield of the reaction was 82.1%, what mass in grams of eliminating reactant would be required to yield an actual amount of 80.25 grams of aluminum? Now I'm just trying to work it backwards. I know my percent yield equals my actual over my theoretical times 100%. So I want a percent yield of 82.1%. I want my actual yield here to be 80.25. So I'm just trying to algebraically rearrange this to solve for the denominator. You should get a theoretical yield of 97.7 grams. Okay. Now, if you're good, this is the last part of the video. You're good to end. If you're not good on the algebra here, let's talk about it. I took that 82.1 and divided it by 100. So this had 100 times 80.25 grams over, we're going to call it TY for theoretical yield. So I divided both sides by 100. Okay. So that canceled out the 100 there and gave me 0.821 here. So I've got 0.821 is equal to 80.25 over theoretical yield. I then multiplied both sides by theoretical yield. So that canceled this out in the denominator down here. Giving me 80.25 grams. is equal to my theoretical yield times 0.821. So then I just divided by both sides by 0.821. To isolate my theoretical yield. And I got the 97.1 gram or 97.7 grams based on my 3 sig figs. 3 sig figs because of this. The 100 is an exact number.